FIR filter design. We have already learned the IIR filter design. Now we'll see FIR filter design. So in this module, we will see some basic concepts like FIR filter, how it is different with the IIR filter. Then how to design the linear phase FIR filters. What are the different characteristics of FIR filter, linear phase FIR filter, frequency response, then designing of FIR filter using different windowing techniques, rectangular window, having window, done different windows, and the FIR filter design using Fourier series method and also frequency sampling method. So totally linear phase FIR filter characteristics including frequency response. Then next question is using window techniques. Third question is using Fourier series method. And next fourth question is FIR filter design using frequency sampling method. That's it. These are the concepts we are going to learn in the fifth model. Of course, the second half of the fifth model is about the DSP processor. That is a separate part. Okay. So let us see first what are the advantages of FIR filter. So over IIR filters, we will see what are the advantages. Sometimes we will ask in the examination what are the differences between FIR and IIR filter, so that you can easily write the differences. So the first advantage is relatively it is very easy to decide compared to IIR filter because it is having only the forward path diagram. That means there is no feedback. It is simply like an open loop system. So we already know open loop system design is very easy compared to the closed loop system. So here FIR filter is like an open loop system. And there is no feedback here. But whereas in IIR there will be feedback. So that wherever the feedback is there, that filter type of filter is called the recursive filter. So yeah, FIR filter is a non-recursive filter, IIR is a recursive filter. But FIR filter, one more advantage is wherever you want to design in non-recursive fashion, you can design recursive and non-recursive, both you can design. If they don't know the feedback, we can create it quantity wherever is required. That is the advantage of this FIR filter. Okay. And it is more computationally efficient because open loop there is no much feedback connections, no much calculations. And next advantage is FIR filters are implemented in hardware and software. Anywhere you can implement it very easily. Of course, IR filter you can easily implement, but compared to IR filter, it is easy to implement in both hardware and software because it is not having any recursive circuit. And next advantage is it follows the linear phase. So very easy to design the linear phase filter using IR filter. Okay. And linear phase property implies that phase is a linear function. So linear phase filter is nothing but its phase is linear like this. Eta of omega is equal to minus alpha omega, where alpha is a constant. So it is related with frequency in a linear fashion. So this is the linear phase filter response. Okay. So that way it is very easy to design using FIR filter. And in IR filter that is very difficult because of feedback connection. And the FIR filter output is delayed by the same amount of the time for all frequencies. That is the linear phase incidence. And thereby it will eliminate, because of the linear phase design, it will eliminate the phase distortion, also called the group delay. Because always will maintain the group delay as a constant. So to reduce the phase distortion, Since it is the linear phase, whenever there is a glitch also, that will be easily removed. And next advantage is FIR filters are always stable because it is a open loop kind. Open loop system is more stable than the closed loop system. So it is always stable. There is no feedback. There is no recursive in nature. Therefore, FIR filters are always stable, or you can say more stable than the IR filters. So for every finite input, you will get a finite output because the name itself is a finite impulse response. It won't be infinity. And the next advantage is it is in linear phase filter. The filter length is equal to a finite value, that is n. So the number of operations are n by 2 only. So because of will be the complex conjugates. It's a multiple of that. So you can get only n by 2 operations. And if you come to the disadvantages of FIR filter compared to IR filter, they require more memory because it's a finite length. No, so whatever if the length is 32 samples you need to store. So memory requirement is more. And the calculations, that many calculations you have to write even in the algorithm. So that is the drawback here. But in IR filter, if you write a single loop, that is enough. It's continuously repeat the same thing, same thing for infinite times. So even the memory requirement is very less. Only one loop samples you need to store it. Remaining is every time it will take from the same bank. Okay, and therefore because of this memory requirement, it is practically is not convenient to implement the FIR filters if it is of more lengthy. And next is the for a desired frequency response with tight constraints on the pass band and the transition band and pass band, a FIR filter may be having large number of coefficients. Based on these values, you will get the order of the filter now. So based on these constraints, it is very difficult to implement with a large number of coefficients. That increases the memory requirement. Thereby more arithmetic operations required and more hardware components required in the FIR filter design. Whereas this IR filter, just that is because of the feedback connection that many coefficients no need to store and hardware requirement also less. And we will see now the linear phase FIR filter. First, I'll stop here. I will start the linear phase FIR filter, how it will be and what are the characteristics we need to study for the linear phase FIR filter. Linear phase FIR filter. Linear phase filter is nothing but the phase response theta of omega is linear. Phase response is linear, simply to say. The phase response is nothing but the relation between the phase angle of the filter and the frequency. So this kind of nature. If the filter is showing this kind of response, then you can say this filter is a linear phase filter. So from this, if you want to write the mathematical expression, this theta of omega is equal to the slope into, suppose if you say the slope is alpha and it is a negative slope, so slope is minus alpha into omega. This kind of relation is called linear relation. So wherever which filter will follow this linear phase relation, that filter is called the linear phase filter. Of course, sometimes this may not be exactly start at zero. Sometimes it may start at drift. There may be a drift. So that time theta of omega can be written as sometimes this kind. This is also a linear, but there is a drift here. If you say that drift is some constant amount, therefore it is minus alpha omega plus beta. So this is also a linear relation. So first we'll see the characteristics of linear phase filter. First in this case and second in this case. Okay. So we will see first what are the characteristics of linear phase filter. Characteristics of linear phase FIR filter. So for this linear phase FIR filter characteristics, we will take what first the frequency response. What is the frequency response? H of e power j omega is equal to, this is the filter. Whenever you see the h of e power j omega, we call it as a filter response. Filter response. That means whenever you apply the impulse input, that is the impulse response. That is indirectly called as a filter response or system function of the FIR filter. So this is given by, since this is the DTFT formula, we have the formula for DTFT. What is the formula? N is equal to 0 to, since it is a finite impulse response, the number of samples in the infinite, the impulse signal is equal to a finite value. So say that finite value as n. That means n number of samples are there in the impulse response. Therefore, this limit is from n is equal to 0 to n minus 1. So n minus 1. N minus 1, 0 to n minus 1. So total h of n is having n minus 1 samples, 0 to n minus 1. So the formula is now summation n is equal to 0 to n minus 1, h of n into e power minus j omega n. Okay. And see, this is the periodic sequence with the period 2 pi, with period 2 pi, because it is DTFT formula, the output, even the input sequence is in the discrete fashion, output is in continuous domain. So omega is in continuous domain only. Therefore, omega is from minus infinity to infinity only. It's with a period of 2 pi. Therefore, this frequency response is split into magnitude and phase responses. So the magnitude response of this is equal to, magnitude response of this is equal to the mode of this. Of course, without this h of n we can't write in detail, but we can write. So for, at this moment, h of is a combination of magnitude response and phase response. So h of e power j omega can be written as mod of h of e power j omega at an angle of h of e power j omega. Okay, this angle can be written as mod of h of e power j omega. Of course, this may be plus or minus, but whenever you want to take the magnitude, that will be positive only. So in reverse, if you want to write, it may be positive or negative, you can write it. And this angle can be written as e power j theta of omega. Here theta of omega is the phase angle. Theta of omega is the phase angle. So phase response. Okay, now here theta of omega will decide the linear characteristics of the phase. So in order to study the linear phase FIR filter, we need to check the two characteristics. The characteristics of linear phase filter are, one is phase delay and second one is the group delay. The phase delay is defined as, phase delay is denoted by TP. It is given by minus theta of omega by omega. Okay, so whatever the phase, from this phase, if you can find out the phase delay, and this, if it gives a constant, then this phase response is called as linear phase response. So from the phase delay, you can find out whether the FIR filter is the linear phase filter or not. Similar way from group delay. So group delay is equal to minus d of theta of omega by d of omega. Sometimes it may not be phase delay constant always, but group delay must be constant in order to avoid this phase distortion. So at least if this is group delay is constant, then we can say theta of omega is a linear phase filter. But here, whenever only the group delay is constant, then the theta of omega is a linear relation, but having some initial shift. Whereas both are constant, then theta of omega is not having any initial shift. It is having directly linear relation from 0. Okay. Now we will see for this, if this is happened, just to check this phase delay and group delay. If theta of omega is equal to minus alpha omega, what happened to TP? Phase delay is equal to minus theta of omega by omega. That gives you minus alpha omega by omega. So minus of minus plus, omega cancel. So this will give you simply plus alpha. It is a constant slope of the response curve. And similar way, what about the group delay at this point? It is minus d of d by d omega of theta omega. This is equal to minus d by d omega of minus alpha omega. This is equal to d by d omega of omega will be 1. So minus of minus alpha is equal to plus alpha. So it is plus alpha constant. Therefore, at this phase angle, if the phase relation is like this, then the phase delay and group delay both are constants. These are the characteristics. In reverse also you can say phase delay and group delay both are constants. Then the phase response is like this. That constant value into minus of that constant into the omega. That is the phase response of the FIR filter. Suppose this phase response theta of omega is equal to beta minus alpha omega. That means just minus alpha omega is shifted by amount of beta. And this, at this point, the phase delay is equal to minus theta of omega by omega. That is equal to beta minus alpha omega minus alpha by omega. This is not giving any constant. This will give you minus beta by omega plus alpha, which is not equal to a constant. Still, it is in terms of omega. So here phase delay is not constant. And group delay, it is minus d by d omega of theta of omega. This is equal to minus d by d omega of beta minus alpha omega. This is equal to, so beta is, if you derivative with respect to omega, it will be 0. The next term is minus of minus, it will be plus. Alpha is constant, take it out. Then d omega by omega will give you 1. So it is a constant. So even the phase delay is not constant, group delay is constant only. That means whenever you require only the group delay is constant, you don't bother about the phase delay, then you can produce this kind of phase response from the FIR filter. You can use this. Okay, so these are the phase response characteristics of the linear phase FIR filter. Now, any doubt here? Sirisha, are you there? Sirisha, are you there? Harshad,
Yes,
are you there?
yes, sir.
What happening? Nobody is responding, Harshad, today. Any problem? Getting bored?
No, sir. No, sir.
Wrote exam well, right?
Yes, sir. Yes, sir.
Okay. Shall I continue? As you need any break after the exam?
Yes, sir. Yes, sir. 10 minutes breaks.
Okay, that you should tell na at the beginning itself. Okay.
Yes.
Okay, please, all of you take 10 minutes break and come back. Okay. I
Thank
will
you.
start at 10:40. Yes, guys came back. Arshad?
Yes, sir.
Yeah, everybody came back.
Yes, sir. Yes, sir.
Okay, I'll continue.
Yes, sir.
Okay, these are the characteristics of linear phase FIR filter, group delay and phase delay. Now, with this linear phase characteristics, let us find what is this constant, how the impulse response should be there for the linear phase FIR filter. Yes. Suppose we define the FIR filter with linear phase. First case, theta of omega is equal to minus alpha omega. We already calculated this Brilliant phase delay. Now we take the magnitude response and phase response. We already know that from the DTFT formula, summation n is equal to 0 to n minus 1, h of n into e power minus j omega 1, that is equal to magnitude response and the phase response. Just with this is like a complex number, definitely you will get some magnitude and phase. So we can write like this. From this, we are going to get the linear phase condition. So to show the FIR filter this kind of characteristics, how should be and what are the conditions to be applied. So for this, I will just expand this exponential term. Summation n is equal to 0 to n minus 1, h of n into cos omega n minus j sin omega n is equal to the magnitude and phase we write as it is. But here also e power something is there. I can split again this as cos theta of omega plus j sin theta of omega. Okay, here now we compare both sides, the real part and imaginary part. This is the real part and this is the imaginary part. So we can write, we can compare both sides, real part and imaginary part. Then we can write it as summation n is equal to 0 to n minus 1, first real part, into cos omega n. This is equal to plus or minus mod h of e power j omega into cos theta of omega. Okay, this is the first equation. And similar we compare the imaginary parts, both sides. Then this is minus. So minus summation n is equal to 0 to n minus 1, h of n into sine omega n is equal to this is plus or minus mod h of e power j omega into sine theta of omega. This is second equation. Okay, now from this second equation by first equation I will do, so that I will get tan here. So in such a way that I am doing 2 by 1. So I am dividing, therefore I will get some equation in terms of the theta of omega. Therefore 2 by 1 I will do. It is minus summation n is equal to 0 to n minus 1. Is there here h of n into sine omega was there. Correct? Sine omega divided by summation n is equal to 0 to n minus 1, h of n into this is cos omega n is equal to this side, RHS side we have sine theta of omega, um, Sorry, mod is there, but mod will be cancelled. Okay, anyhow, I'll write that step also. So here it was mod h of e power j omega into sine theta of omega divided by, of course, plus or minus mod h of e power j omega into cos theta of omega. Here these two cancel. Therefore, this is equal to tan theta of omega, but we don't write tan theta of omega because this much, if it is constant, simply we can take it theta of omega is equal to tan inverse of this, but it is not a value. It is again an expression. So in order to simplify that, I will do cross multiplication. Therefore, what I'll get is minus summation n is equal to 0 to n minus 1 h of n into sine omega n into cos theta of omega is equal to summation n is equal to 0 to n minus 1 h of n into sine theta of omega, cos omega in n into sine theta of omega. Right. Here, I will substitute if the response is theta of omega. Since theta of omega is equal to minus alpha omega, then I will take this equation as summation n is equal to 0 to n minus 1 h of n into sine omega n and cos of minus alpha omega is equal to summation n is equal to 0 to n minus 1 h of n into sine theta, here cos omega n I will write first. Then sine theta of omega is equal to sine of minus alpha omega. Okay, here sine of minus alpha omega is nothing but it is minus sine. So here minus is already there, we can cancel it. But here cos of minus omega will be cos omega. Cos minus theta is equal to cos theta only. No? Therefore, it is written as minus summation n is equal to 0 to n minus 1 h of n into sine omega n into cos alpha omega. Okay, is equal to minus summation n is equal to 0 to n minus 1 h of n into cos omega n into sine alpha omega. Okay, so minus minus cancel. Then here I can write it as this total part I can move to left side only. Then summation n is equal to 0 to n minus 1 and here h of n common is there. I can take common h of n. Therefore, remaining term is sine omega n cos alpha omega minus cos omega n sine alpha omega, right, is equal to 0. See, what is this formula? Sine A cos B minus cos A sine B. What is the formula? Anyone? Sirisha? Cos sin A cos B minus cos A sin B formula. Sandhya? Priyanka?
Yes, sir.
Priyanka, what is this formula?
Sin of A minus B.
Sin of A minus B. Okay, then sin of omega n minus alpha omega is equal to 0. Here omega also you can take common, no? I will take common. Summation n is equal to 0 to n minus 1 h of n into sine of n minus alpha. N minus alpha. Otherwise, I'll take minus of alpha minus n into omega is equal to 0. Since sine of minus theta will be minus sin theta, and this minus this I can throw to outside. Therefore, still I can write summation n is equal to 0 to n minus 1 h of n sine of alpha minus n into omega is equal to 0. Therefore, this part is equal to 0. Therefore, summation n is equal to 0 to n minus 1 h of n into sine of alpha minus n into omega is equal to 0. So, therefore, from this we will get what is the condition, what is the alpha value. In order to get this data of omega is equal to minus alpha omega linear phase, this alpha must be constant. So we will test it whether alpha is constant. If it is constant, what is the value? Okay. In that, what is the condition to satisfy this equation? So in order to satisfy this condition, we will expand this series. So it can be written as n is equal to 0 means h of 0 into sine of alpha omega plus h of 1 into sine of alpha minus 1 omega plus h of 2 into sine of alpha minus 2 into omega plus and so on plus h of n minus 2 into sine of alpha minus n minus 2 into omega plus h of n minus 1 into sine of alpha minus of n minus 1 into omega is equal to 0. Okay. Okay. Let me continue this. See, if you want to satisfy this equation, this h of 0, this term, or actually the whole terms must be cancelled in order to satisfy this. Then only we'll get 0. Otherwise, either all sine terms must be equal to 0. Otherwise, all samples must be equal to 0. But all samples will not be 0 because if some impulse signal itself is 0, then impulse response will be 0 means total system filter is not is there. So filter is not there means no need to design it. So it will not happen. At the same time, all sign will not be equal to 0 always, or at angles. Therefore, all terms will not be equal to 0. There, ultimately, what we should we try for cancellation of the terms. Therefore, in order to do that, how to get cancel? You assume that h of 0 is equal to h of n minus 1, this term. In order to get cancel, okay, and if these two are equal and this sine alpha omega is equal to minus of this sine of alpha minus of n minus 1 omega, then see these two terms are negative but equal. This h of 0 is equal to h of n minus 1. So this last term and this last term we can cancel it. Right? So then we can get cancellation similarly. Next h of 1 is equal to h of n minus 2, these two terms, and also sine of alpha minus 1 into omega is equal to minus of sine of alpha minus n minus 2 of omega. Okay, so if these conditions satisfy, then these terms will be cancelled and finally you will get 0. So and so on you can do. And in general, this can be written as h of n is equal to h of n minus 1 minus n. Okay, so by seeing these terms, we can write in general h of n is equal to this much. And also in general, if you see this sine of alpha minus n omega is equal to, how can you write this is equal to minus of sine of alpha minus of, this is n minus 1 minus n of omega. Okay, now by this we can simplify and we can get some alpha value. So here from this we can't get alpha value, but from this you can get, you can try to get. So I will write this separately. Since sine of alpha minus, what is that, alpha minus n into omega, alpha minus n into omega is equal to minus of sine of um, alpha minus of n minus 1 minus n into omega. Since minus, if you want to throw inside, you can take it sine of minus alpha plus of n minus 1, sorry, minus n into omega. Now sine you can remove it. So we can make it equate these angles. Therefore, alpha minus n into omega is equal to minus alpha plus n minus 1 plus, sorry, minus n into omega. Now omega cancel. So what we got is alpha minus n is equal to minus alpha plus n minus 1 minus n. Minus n minus n also cancel. Therefore, here one alpha is there, here one alpha. So I'll take this alpha also to the left side. Therefore, it is alpha plus alpha is equal to n minus 1. Therefore, 2 alpha is equal to n minus 1. From this, we can get alpha is equal to n minus 1 by 2. Right? This is the condition for the linear phase FIR filter. And from this, what we can understand, this is a constant, so that the filter is phase response is linear. Okay, and this alpha value is equal to n minus 1 by 2, means where n is the number of samples present in the impulse response h of n. So n is equal to length of h of n. Okay. Now from this, what we can say is, for the linear phase FIR filter are to become TP and TG. Both are constants. To in order to do this, to be TP and TG constant, H of n of the impulse response of the FIR filter must be equal to H of n is equal to H of n minus 1 minus n, and also alpha is equal to n minus 1 by 2. These are the two conditions to be satisfied in order to get the constant phase delay and constant group delay. Okay, guys, understood this point? Arshad, understood? Priyanka, till this point, any doubt? Hello, Priyanka? Anybody is there?
Yes, sir.
So far, any doubts?
No, sir.
Okay. Okay. So these are the conditions for the TP and DG constant. Here also, the phase, if you want to write this, this symmetry, this is called alpha value constant. This constant may be an integer value, or here and a floating value. That depends on capital N value. So again, this value, based on this value, I mean, this depends on N value, we can get two different kinds of the impulse response. We can show two different types of impulse response based on the N value. So in that, the first case is N value may be even or odd. Suppose if it is even, what will happen? If it is even, for N even, that means, say, for example, n is equal to 4 samples in h of n. So what we can write from this, h of 0 is equal to h of 4 minus 1, 3 minus n. That means 0. So it will be equal to, mean 4 samples. I will actually note it. This is the first sample. So this is the second sample and third sample. Again, fourth sample. 4 samples are there. Okay. So this sample must be equal to the last sample in order to satisfy this. If I use like this h of n, it is not useful. So I should make this h of n sequence. As you select this h of n sequence, such as h of n is equal to h of n minus 1 minus n. That means it is symmetry. That means wherever h of 0, that will be equal to h of 3. This is a 3. Okay, and this point should be equal to this point. So this is the graphical representation of this condition. Okay, and where alpha is equal to n minus 1 by 2. N minus 1 by 2 here is 4 minus 1 by 2, it is 3 by 2, 1.5. That means this alpha represents, this alpha is equal to 1.5 represents the center of this h of n sequence. So it is center of symmetry. H of n sequence is a symmetrical sequence with the center of symmetry of alpha is equal to n minus 1 by 2. So this way we can say this condition in a graphical way. Suppose, for example, this h of n value is not even, it is odd value. Then for odd value, n odd, for example, n is equal to take 5 samples. Then this is having 5 samples, 0, 1, 2, 3, 4, 5 samples. Take this is the first sample and second sample. This sample must be from this equation, h of 0 must be equal to h of 4. Right? You can see this. 5 minus 1, 4 minus 0, which is 4. Similarly, h of 1 is equal to h of 3. that way. So h of 0 must be equal to h of 4 and h of 1 must be equal to h of 3, and this h of 2 may be any value because there is no another point here, and alpha value here 5 minus 1 by 2, it is equal to 2. That means center of symmetry is exactly at the half of the center of the impulse response. So it is giving equal parts, but the center of symmetry is the middle sample. So this is alpha is equal to n minus 1 by 2. Okay, here this h of n is still the symmetric and the center of symmetry is exactly n minus 1 by 2, a and n is middle of the h of n sequence. Okay, so simply after getting this condition, I'm just showing how the impulse response will be for different n values. If you have even number of samples, this is the kind of h of n, and for n in r, this is kind of h of n. But the times how it will be the center of symmetry. Now we will see here from this we can we got two conditions. For n is equal to even, how the impulse response and what is the center of symmetry, and for n odd, what is center of symmetry, what is the h of an impulse response. And these two conditions we got for linear phase filter where theta of omega is equal to minus alpha omega. But we have one more case, the second case, theta of omega is equal to minus alpha omega plus beta, right? If you take this linear relation, that means only tz is constant, there is no, but tp is not constant. Okay, at this point what will be the condition for the impulse response and what is the center of symmetry, we will calculate now. In this case, we got previously summation n is equal to 0 to n minus 1 h of n sin omega n divided by summation n is equal to 0 to n minus 1 h of n cos omega n. This is equal to sin theta of omega divided by cos theta of omega. Right now, after cancelling the magnitudes. Here I will substitute this theta of omega is equal to this much. Previously we substituted only minus alpha omega. Now we will substitute minus alpha omega plus beta. So this is equal to sin of minus alpha omega plus beta by cos of minus alpha omega plus beta. Now this we cross multiply and we'll get. Therefore, after cross multiplication, we will get summation n is equal to 0 to n minus 1 h of n sin omega n into cos of beta minus alpha omega is equal to summation n is equal to 0 to n minus 1 h of n into cos omega n into sin of beta minus alpha omega. Okay. Now we'll take this total to this side. Then what can I write? Minus you can take common and leave it. So it is equal to summation n is equal to 0 to n minus 1 h of n, take common, then remaining is sin omega n into cos of beta minus alpha omega plus, if you take this side it will become minus, so minus minus is taken common and remove it. So it is cos omega n into sin of beta minus alpha omega is equal to 0. Therefore, this can be written as summation n is equal to 0 to n minus 1 h of n into this can be written as cos A sin A cos B plus cos A sin B. The formula is sin A plus B, sin of A plus B. So it is written as sin of omega n plus beta minus alpha omega is equal to 0. Okay. This further can be rewritten like h of n into, here I can write first beta minus of, here alpha I'll take, sorry, minus I'll take common. So alpha minus n into omega I can write is equal to 0. Okay. Now, for example, if suppose say beta is equal to some pi by 2 value, shift no. So in phase shift, I write it as pi by 2 is the phase shift. Therefore, this can be written as summation n is equal to 0 to n minus 1 h of n into this, sorry, this is sine of pi by 2 minus something. Sine pi by 2 minus theta will be written as sine, sorry, sine pi by 2 minus theta is cos theta. Since sine pi by 2 minus theta is the cos theta, by this we can write this is equal to cos of alpha minus n into omega, okay, is equal to 0. Now we will expand this and we'll find the conditions. So expansion will give me h of 0 into cos alpha omega plus h of 1 into cos of alpha minus 1 omega plus and so on, plus h of n minus 2 into cos of alpha minus of n minus 2 into omega plus h of n minus 1 into cos of alpha minus of n minus 1 into omega, okay, is equal to 0. Then in order to satisfy this equation, previously we tried to do this is equal to minus of this, but here cos and cos, even you take the minus angle, it never become minus. Therefore, instead of trying this and this is opposite, we'll make it now these constants are opposite. That means h of 0 is equal to minus of h of n minus 1, and this cos will make it equal. Cos omega is equal to cos of alpha minus of n minus 1 omega. Okay. Now, similar way, second term h of 1 is equal to minus of h of n minus 2 and cos of alpha minus 1 omega is equal to cos of alpha minus n minus 2 omega. Sorry, omega, whole omega. Okay. Now, from this, in general, what we can write h of n is equal to minus h of n minus 1 minus n. This is a condition for the impulse response to produce the linear relation with a group delay constant. And from this, what is the general notation you can write? Cos of alpha minus n into omega is equal to cos of alpha minus of n minus 1 minus n into omega. Okay. From this, therefore, we can write this cos and cos. If we remove it, we will get alpha minus n into omega is equal to alpha minus of n minus 1 minus n into omega. So omega cancel, and this minus n cancel. Then what you get? Alpha is equal to this is beta minus alpha. So here you can write minus of minus alpha because it is getting cancelled here. So cos minus theta is also equal to cos theta only. So in that case, you can write cos theta as cos of minus theta. So you will get here, I think one more step I will write. It is cos of alpha minus of n minus 1. Right, this is okay. From this, by using this condition, I can write this is equal to cos of alpha minus n omega is equal to cos of minus alpha plus of n minus 1 minus n omega. You can write because cos of minus theta is equal to cos theta. Because if I don't use this, alpha is getting cancelled here. That's why I'll put minus. So it is minus alpha plus n minus 1. Therefore, if I move to this side, then it will be 2 alpha that is equal to equal to n minus 1. Therefore, alpha is equal to n minus 1 by 2. So center of symmetry again you got at n minus 1 by 2 only. It is called center of symmetry. Center of symmetry. Okay. And the condition here for the group delay for Tz is equal to a constant. The conditions are h of n must be equal to h of n minus of h of n minus 1 minus n, the first condition, and second condition is alpha is equal to n minus 1 by 2. Okay, in this case, in order to this is called antisymmetric. Here from this condition we can understand the impulse response is antisymmetric. So the antisymmetric h of n will be depending on here, you can show in a graphical way for different n value. If n is even case, the antisymmetric h of n is like this. So it is suppose say n is equal to, for example, 4. So we have 4 samples. 1, 2, 3. So whatever I fill here, if it is 1, so say suppose 2. So this h of 3 also must be equal to 2, but in negative is minus 2. And the next h of 1 is equal to 1, means this will be minus 1. This should be minus 1. Okay. Here, center of symmetry is exactly the half, midway. This is alpha is equal to 4 minus 1 by 2. It is 3 by 2. That means 1.5. And for n is equal to odd, if for example you take 5 samples. So h of n is having 5 samples. 1, 2, 3, 4. So antisymmetric in the sense, you take one sample here, and the last sample will be in opposite direction, minus 2, and this is at plus 1, and this is at minus 1, and this may be any value because it is, but because in order to cancel this, make this is equal to 0. So then only equation will be satisfied. Okay. So these are the conditions for the linear phase FIR filter. Nice. if they ask in the examination for 8 marks, explain the characteristics of the interface FIR filter, we should do this. But may not be full derivation, but at least one derivation you can show, and the remaining case we can show it a similar way. This you will get. That way you can show it. Any doubt so far in this question? Priyanka, any doubt here?
No, sir.
Okay. So let's start next topic. The next topic is the linear phase. So FIR filter frequency response. So frequency response of linear phase FIR filter. The frequency response includes magnitude response and phase response, but here phase response is always linear, that is fixed now. Either this or theta of omega is equal to beta minus alpha omega, either of this. So anyhow, both are the linear phase filters only. But mainly in this frequency response, we have to find how the magnitude plot, how the magnitude response of the linear phase filter will be. Okay, that is the point. So for this, we will study the magnitude response for different cases. In the previous characteristics, we found 4 cases, and that one is n odd, h of n symmetric, and n even, h of n antisymmetric. I will write it in different way. N h of n. N is odd or even. For n odd, h of n may be symmetric. For n or even, n it may be symmetric. For n odd, h of n may be antisymmetric. And for n even, it may be antisymmetric. So we can see 4 cases here. So in these 4 cases, we will study what is the frequency response, means focused on the magnitude response. We will test. So out of these 4 cases in the examination, you may get 1 question. Okay, now we will see, we'll start with the first case. Case 1. The first case is, today I will give you only first case because by that time will be over. So first case is symmetrical impulse response. Symmetrical impulse response, that is h of n, and n is odd. So for this case, we will derive the expressions and the magnitude response. So the frequency response of the linear phase FIR filter or FIR filter is given by h of e power j omega is equal to summation n is equal to 0 to n minus 1 h of n into e power minus j omega n. Now this can be splitted. So in order to find the magnitude response, we need to apply all these conditions for h of n is symmetric and n is odd. For this case, n is odd, okay, and n is odd means, for example, if you take one h of n sequence for n is equal to odd 5 samples, when it is symmetric, this point 0, 1, 2, 3, 4. This sample and this samples must be equal. This sample is equal. This must be equal to in the middle, a constant value. So this point, exact. This is the called symmetry point, alpha value. At this alpha, we will get the center of symmetry. So this total h of n sequence can be divided into three parts: first part, second part, and middle part. So the samples, h of n samples can be divided into three parts. So I will divide this summation into three parts. One is 0 to, this is equal to n minus 1 by 2 point, this n value. Okay. And what about this before sample? It is, this sample is n minus 1 by 2 minus 1 sample. And this sample, this point n value is equal to n value. This n value is equal to n by n minus 1 by 2 plus 1. Okay. So the summation limits are applied and given like n minus 1 by 2 minus 1 h of n sequence e power minus j omega n plus next middle sample, that is equal to h of n minus 1 by 2. Directly I can write it into e power minus j omega of n minus 1 by 2 plus third term is summation n is equal to, starting is n minus 1 by 2 plus 1 to n minus 1 into h of n into e power minus j omega of n minus 1 by 2. Okay, sorry, e power minus j omega n only. Okay, so we have half samples here and middle sample here, rest of the half samples, last half samples here. So this is the way you can write it. Now I will, okay. Now this can be simplified. See, limit, summation limit in the top n minus 1 by 2 minus 1. It can be written as summation n is equal to 0 to n minus 3 by 2. Correct? If you taking LCM into h of n e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2 plus summation n is equal to, this is equal to n plus 1 by 2 to n minus 1 into h of n into e power minus j omega n. Okay. Here, in order to get the impulse magnitude response, we need to find this is equal to in terms of DTFT and this also in terms of DTFT formula. So for that I will change the limits. So for that I will put small n is equal to n minus 1 minus p. I will assume. Therefore, this is for second limit. First limit I don't change so far because I need to change the limits of the second term only. This is starting only, this also we can shift it because the second half is exactly the same samples in reverse direction as the first half. So I can change a little bit and if possible I can club this to first half. Therefore I'm trying for that. For that I put n is equal to n minus 1 minus 3. Then as summation limits of second summation limits, as n tends to n plus 1 by 2, this P tends to, from this P is equal to n minus 1 minus n. P tends to, how much it will be? N minus 1 minus n plus 1 by 2. This will give you 2n minus 2 minus n minus 1. So it will give 2n minus n. It will give you minus n. And this is minus 2 minus 1 minus 3 by 2. And next upper limit as n tends to n minus 1, this p tends to 0. Therefore, now the limit total h of e power g omega can be written as summation n is equal to 0 to n minus 1 n minus 3 by 2 h of n into e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2 in plus last summation limits change now. P is equal to 0 to, sorry, this is limit n minus 3 by 2 to 0. And here h of n is equal to n minus 1 minus p and e power minus j omega of n minus 1 minus p. Okay, this is equal to, here in place of p again I can replace small n. Therefore, it will be equal to summation n is equal to 0 to n minus 3 by 2 h of n e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2 plus the summation limits also can ulta. We can do it. So summation n is equal to 0 to n minus 1 by 3 h of n minus 1 minus n into e power minus j omega of n minus 1 minus n. Okay. Now we know that for this case, h of n is a symmetric. That means h of n is equal to this h of n minus 1 minus n. Therefore, since h of n is symmetric, that is h of n is equal to h of n minus 1 minus n. The previous equation can be written as is equal to summation n is equal to 0 to n minus 3 by 2 into h of n e power minus j omega n plus h of n minus 1 by 2 e power minus omega of n minus 1 by 2 plus summation n is equal to 0 to n minus 3 by 2 h of n into e power minus j omega of n minus 1 minus n. Now this h of n is same. Limits also same. So I can club these two. Therefore, summation n is equal to 0 to n minus 3 by 2 h of n into e power minus j omega n plus e power minus j omega of n minus 1 minus n plus this term as it is you keep it h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2. Okay. Now we have e power minus something and something. Here in order to get a cos or sin from this, I can do something. So that is just take common from this e power come from this you take common e power minus j omega of n minus 1 by 2 from these two terms. Therefore, Since it is not taken common, I mean, it's extra term, I should extra use g power j omega of n minus 1 by 2 for this term into e power minus j omega n. Similar way to this also extra I should do it. E power j omega of n minus 1 by 2 into e power minus j omega of n minus 1 minus n plus as it is this term you write it h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2. Now from this is a constant, you can take it out of from the summation, and here inside these two terms you can take common, e power minus e power j omega you can take common, here also e power minus j omega you can take common. Therefore h of e power j omega is equal to e power minus j omega of n minus 1 by 2 we have taken common from summation n is equal to 0 to n minus 3 by 2 into h of n is a common into e power j omega if you take common it is n minus 1 by 2 minus n, and from the next term e power minus j omega you take common because we need to get e power j omega one time, second time e power minus j omega, so I'm taking like that. So it is n minus 1 minus 1 so minus n plus sorry minus of n minus 1 by 2 greater plus okay, so it is h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2. Okay, now this is equal to e power minus j omega. From this and this both you can take common, you can take common it. So it is total common summation n is equal to 0 to n by 3 by 2 h of n into, here this is okay as it is you write e power minus j plus j n minus 1 by 2 minus n plus here it is e power if you take LCM here this is like 2n minus 2 minus 2n is 2n minus minus n minus n plus 1 whole divided by 2. Okay, this is equal to 2n minus n, it will give you just 1 n, and here um, minus 2 plus minus 2 plus 1 it is minus 1 by 2, and this minus 2n by 2 will separate it, so I can write like this. So from this total can be replaced with n by 2 n minus 1 by 2 minus n. So it is e power minus j omega of n by n minus 1 by 2 minus n plus as usual this term h of n minus 1 by 2 into e power minus j omega of n minus 1 by 2. Okay, this is sorry e power minus j omega is already taken common, so we can write here itself. It is h of n minus 1 by 2. Here this total is written as 2 cos of something. So it is minus j omega of n minus 1 by 2 summation n is equal to 0 to n minus 3 by 2 h of n into this 2. So 2 h of n cos omega of n minus 1 by 2 minus n plus h of n minus 1 by 2 as it is. Okay, this is total h of e power j omega. If you compare this with magnitude response, suppose say I will assume the magnitude response is h cap of e power j omega at an angle of e power j theta of omega. If you compare with this, and this also you can take it angle of h cap. Sorry, okay, it's enough. It's okay. Theta of e power j theta of omega. If you assume it, if you just compare it, compare this with this one. Therefore, you what we can get, this total is equal to h cap of e power j omega. Okay, and this is equal to this part. Therefore, from this h cap of e power j omega is equal to summation n is equal to 0 to n minus 3 by 2 h of n. See this h of n minus 3 can also, okay, next step I will write. So it is 2 into h of n cos omega of n minus 1 by 2 minus n n by 2 minus n omega plus h of n minus 1 by 2. Here, with it to generate to and again simplify this, just make it this is equal to p. Therefore, let p is equal to n minus 1 by 2 minus n, because we need the magnitude response, so we need to simplify for better understanding. So this is equal to this much. Then summation limits, the summation limits I will change. Therefore, as n tends to 0, this p tends to n by 2 minus n minus 1 by 2. And as n tends to n minus 1 by 3, this p tends to n minus 3 by 2. So it will be n minus, sorry, n cancel. It will be equal to n minus 1 by 2 minus n minus 3 by 2. So it will give n minus 1 minus n plus 3. So it is 2 by 2. 2 by 2. It is equal to 1. So if you apply these limits assumption in the above equation, this therefore h cap of e power j omega can be written as summation b is equal to n minus 1 by 2 to 1 2 into h of now n is equal to n minus 1 by 2 minus p, shifted one, impulse response, then cos of omega p, p omega, plus h of n minus 1 by 2. This is constant, you can keep it as it is. Now this can be written as, again in place of n you can keep p, again back it to n. So it will be written as n is equal to summation limits you can ulta. So this is n is equal to n minus 1 by 2, 2 into h of n minus 1 by 2 minus n into cos of omega n plus h of n minus 1 by 2. Okay, here see this is in the shape same value, like if you keep it n is equal to 0, this will come. Therefore, instead of starting and cos omega n, if you substitute n is equal to 0, cos 0 will give 1. Okay, so instead of this I can write I can write this total as summation n is equal to 0 to n minus 1 by 2. This total I will write it as a of n and cos omega n I'll place it. Where when a is equal to 0, n is equal to 0, a of 0 must be equal to this much. But from n is equal to 1, this a of n value must be equal to 2 into this much. Where I can write clearly, where a of 0 is equal to, a of n value, a of n value is equal to, a of n is equal to h of n minus 1 by 2 for n is equal to 0. It is equal to 2 into h of n minus 1 by 2 minus n for n is not equal to, or n is greater than 0. That means from n is equal to 1. So this is the a of n value. And from this is the h of e power j omega, that is treated as the magnitude response of the linear phase FIR filter. So whereas the phase, when you compare the phase angle, one second, maybe it is stopped at 20 pages over. I will, one second, I will show this. So I'll take one more whiteboard. Okay. Now theta of omega is equal to, theta of omega is equal to, from this e power, we have denoted e power j theta is equal to, we have compared with this omega of n minus 1 by 2, right? So therefore theta of omega is equal to omega into n minus 1 by 2. We know that this is equal to alpha, so it is minus because of this minus. So it is equal to minus alpha omega. This is what the linear phase response. This is already we have assumed. Because of this only we got n is equal to symmetrical and n is equal to odd, and h of n is the symmetric sequence. So therefore, if you draw h cap of magnitude response is equal to summation n is equal to 0 to n minus 1 by 2 a of n into cos omega n. So this is a cos function, and the cos function is varying in between plus and minus. Okay, but h of what we want, the magnitude response of linear phase FIR filter. This is the magnitude response. So this magnitude response is nothing but the magnitude of this. Even it is not having any complex quantity, but still it is varying in between plus and minus because of the cos. Because cos value vary from -1 to +1. Therefore, we need to take mod of this. That is a magnitude response. So in a graphical way, if the magnitude response, this h of e power j omega, this is called zero phase frequency response. Zero phase frequency response. This h cap of e power j omega. Okay, this response, if it is like this sinc function, then the magnitude response mod h of e power j omega, magnitude response of linear phase FIR filter will be like this. For this 1, 2, 3, 4, 5. So you will get all positive or negative, whatever you will get this. For positive, it will get positive only. Negative also, it will get positive. That's it. So same thing here you will get, but instead of this phase negative value, it will get positive. That is the magnitude response of the relay phase FIR filter.